wabarakatuh. My name is Muhammad Waluddin bin Ahmad Syukri. My matric number is AA181788.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman bin Muhammad Rafi'i. My matric number AA180844.
Assalamualaikum. My name is Zulkarnain Ali bin Zulkifli. My matric number is 181471.
Assalamualaikum. My name is Hafiz bin Abdullah. My matric number is AA181519.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syazrul bin Zulkifli. My matric card is AA181797.
Okay, now I will talk about introduction. A PID controller is an instrument used in industrial control application to regulate temperature, flow, pressure, speed and other process variables. PID, which means proportional integral derivative controller, use a control loop feedback mechanism to control process variable and are the most accurate and stable controller. As a feedback controller, it delivers the control output at desired level. Okay, for its application, PID controller can be used in a lot of things. One of it is as a temperature sensor. Controller takes an input from a temperature sensor and has an output that is connected to a control element, such as a heater or fan. When something happens, an appropriate action will be taken by the controller.
Assalamualaikum. Now I'm going to present about the proportional type of linear feedback control system in which a correction is applied to the control variable, which is proportional to the difference between the desired value and the measured value. Second is the response of the controller and the mechanism for affecting the variable make a greater response for a greater differential and a smaller change for a smaller differential. And the three is the power output is always proportional to the error. And lastly is the manipulated variable output is proportional to the system deviation.
Assalamualaikum. So I will explain about integral. Integral is the control mode where the controller output is proportional to the integral of the error with respect of time. So action by a control mechanism that makes a change to the inputs of manufacturing based on the accumulated error over a period of time. So integral controller is often used in conjunction with proportional controller, which make corrective change in proportion to the amount of error in an input in order to make input adjustment faster and more accurate. The rate of change of manipulated variable is proportional to the system deviation.
Assalamualaikum warahmatullahi wabarakatuh. And okay, now we going to the next topic is about directive. Directive is the reaction to the rate at which the error has been changing, and it slow the rate of change of the controller output. Then it give a controller additional action control when the error change consistently. Thirdly, it make the loop more stable, which allows using a higher controller gain and a faster integral. Fourthly, it acts as a brake or dampen on the control effort. And lastly, the output will decrease when the process variable is increased rapidly.
So I will explain about the problem given in our assignment. So this is our modeling equation. So our block. So the modeling equation of the system above is mx plus bx plus kx is equal to f. Then the Laplace transform of the modeling equation produce ms power of 2 xs plus bs xs plus kxs equal to fs. The transfer function between the displacement xs and the input fs then become 1 over ms power of 2 plus bs plus k, given m equal to 1 kg, b equal to 10 Newton and K equal to 20 Newton meter and F is equal to 1 Newton. So on this video we will solve the problem, which we will find how each of Kp, Ki and Kd contributes to obtain the graph that have fast rise time, minimum overshoot and no steady state error.
Assalamualaikum. My name is Zulkarnain and now I will explain about open loop system. Okay. Based on the question given, we have made an equation which is 1 over s squared plus 10s plus 20. So in the question there are some information, so there are some value, so we enter the value into our equation and then we perform our open loop system. Okay, first this is our circuit, and after we run the circuit we get this graph. So the rise time of the graph is 0.867 and the final value is 0.05 and the overshoot is 0.5. So the requirement is we need to have fast rise time, minimum overshoot which is below 5% and no steady state error. So but based on the graph the statistic error is high because the final value is 0.05 and which is mean that 1 minus 0.05 times 100% it will equal to 95%, which mean that the statistic error is high. So but the requirement is we need no statistic error. So at least the statistic error need to be below 2%. So we will show how proportional, integral and derivative will help us to continue to achieve the requirement. Yes.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, next we're going to the P controller. Okay, first in Simulink, there are 5 the value of P that we random choose and apply it in the P controller. First one is P is equal 300. Secondly, P is equal 450. Thirdly, is equal 500. Fourthly, is equal 850, and lastly is equal 1025. Okay. P controller we connect with the transfer function block, and lastly after we connect also to the scope to get the output value the output will show in the graph. So we're going to the closed loop, the open loop. I'm sorry. Okay, in open loop, the rise time and the steady state error are so higher. So when we apply P controller, the rise time and the steady state error will reduce. That's why we need to apply P controller inside. So when we run the simulation of the P controller, we will get the graph output that show 3 points. First one is rise time, second is steady state error, and lastly is about overshoot. Okay, the graph show that we choose the value of P is equal 1025 is because between 5, the value of k, the value of p that we random choose, the best output graph is 1025. It's because the value of error, rise time, and overshoot are connected with the requirement needed. Okay, the steady state error that require is below than 2%. So we get the error, the final value is 0.98. So we calculate 1 minus by 0.98, get the total and multiply with 100% and get 2% for the steady state error percentage. Next, the rise time we can get inside the output is equal 35 millisecond. And lastly, about overshoot is equal 60%. PI controller, when we apply PI controller inside the transfer function, steady state error will decrease. When we apply PI controller increase, so the steady state error will decrease, and rise time will also decrease, and overshoot of percentage increase. So that's why we apply PI controller inside the open loop. Thank you.
Okay, Assalamualaikum. Now I'm going to present about the PD controller. So first, when we look at the PD Simulink, at this we look that it has a both Simulinks. It has both equation, and it has a both. It has two PD controller, PD controller 1 and PD controller 2. So this means that I compare the two graph to make sure that I get the true value graph that I can compare with the KP graph. So when we look at this graph, the first one is the yellow graph at the hover here. So the yellow one, this is PD controller 1, and the blue graph is the PD controller 2. When we look at this, we see that PD controller 1 has more overshoot than the PD controller 2. That is because PD controller 1, I put the KD value is 80, and the blue the PD controller 2, I put the KD value is 100. So this means when we refer to the table that we learn at the class at the control system, PID table, when the D is increased, the value of the overshoot and the settling time will decrease. This means when I put the active KD value for the yellow graph, that means the overshoot is increased. But when I put the more than active the KD value for the PD controller to the blue graph, the overshoot is less than the PD controller 1, that is yellow. So and the settling time for this graph is less than the yellow. So that's mean for both of this graph, from both of this graph, I took the blue graph because the blue graph is less overshoot, and then from requirement we need the overshoot is less than 5%. So the blue graph, that's mean PD controller 2 has the requirement that we need. So now I'm going to compare with the KP graph. When even before I put the KD value into the KP, the graph has a high overshoot. There is 60%. But when I put the KD value, that is from the blue graph, that means KD value is 100. The overshoot from the graph will decrease until 1.5%, and the setting time also decrease from the 0.035 second into 0.015 second. That's mean when I put the KD value 100 into the KP 1025 graph, the value of the overshoot and the settling time will decrease. And then but for the steady state error, it will remain and not change. That value is 2%. If we follow the table, the steady state error for the KD value will remain and not change. Okay, that's all for me. Thank you.
Assalamualaikum. So I will explain about PI controller. So this is our circuit for PI controller. So the value for first controller, P is equal to 1025, which is remain constant. The value of proportional is same as the proportional controller. So the value of integral is 100, and the value integral at second is 400, and lastly it is 70. So this is graph for PI controller. So PI controller, we add the integral to the proportional in order to eliminate a steady state error. As you can see, we already test many value of KI in to find the best value to eliminate the steady state error. So we will choose KI equals 70 because this value will eliminate the steady state error. Other than that, the PI control, the integral can increase the overshoot percentage, depends on what value. So if the KI value, the integral value is higher, then the overshoot percentage will increase. If lower the KI value, if lower the integral value, the lower the overshoot percentage. So here the result for overshoot percentage. As you can see here, when I set the integral value to 700, the overshoot percentage we will obtain the higher overshoot percentage. While integral equal to 100, we will obtain the 100 overshoot percentage. So we can check here. For KI equal 700, the overshoot percentage is 63. If KI is equal to 100, the overshoot percentage is 60. And KI equal to 400, we can see the difference. If Ki equal to 700, the overshoot is 63, and if Ki is equal to 100, the overshoot is 60. So here we can see the higher the integral value, the higher the overshoot percentage. And so how it eliminates the steady state error? So as you can see the graph here, so this is our proportional graph. We already choose the value of Kp equal to 1035, which we will obtain the steady state error percentage is below 2%. So after we add the integral, after we add the integral controller, we will eliminate the steady state error. Here the result after add the I controller to the P. So the base value of Ki is 700, as I said just now, because this value can eliminate the steady state error. And rise time for this graph is 0.35 second, and settling time is 0.823. So how we calculate the steady state error? Firstly, we need to know the value of steady state final value here. We can use the cursor measurement to measure it, and then we 1 minus 1 time with 100, and we will get 0%. If we get 0%, that's mean there is no steady state error. So that's all from me. Thank you.
Ya, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shazrul bin Zulkifli. So I will explain about PID controller. So in this PID controller, this is our circuit. So we state that the value of proportional P is 1025, the value of integral I 700, and the value of D is 100. So this value we can conclude that the P can reduce rise time and steady state. I can eliminate steady state and increase overshoot, and D can reduce overshoot. So after we run, we get this graph. So this graph show that settling time is 0.0396. The rise time is 16.042 milli, and overshoot is 0.083. So how we can show this PID controller, its characteristics. So we compare with open loop circuit. So this is open loop graph. Compared to the PID controller, it shows that rise time in open loop is more slower compared to the PID controller. So next is the final value in open loop is 0.05, which means its steady state error is 95%. So we compare to the PID controller. PID controller, its final value is 1. So it has no steady state error. So we can conclude that this PID controller has no steady state error. It's more its rise time is more faster, and it has a minimum overshoot. So that's all from me. Thank you. Lastly, I will explain about the conclusion. So in this conclusion, I will explain the effect of PID controller. So for KP, A proportional controller will have the effect of reducing the rise time and will reduce but never eliminate the steady state error. For KI, the addition of an integral term of the controller tends to help reduce steady state error. So for KD, the derivative control mode give a controller additional control action when the error change constantly. So we can conclude that the PID controller is the best for each transfer function because we are able to obtain desired graph based on the problem given. So lastly, requirement for problem given are fast rise time, minimum overshoot and no steady state error. That's all from me. Thank you.